This is going to be a relatively short lecture for us. In section 2.2, we're going to talk about graphs of functions. Previous section, we talked about functions themselves. Now we're going to talk about a little bit about the graph of functions. And I have bulleted the things that are of interest to us in this section. We're going to talk about the vertical line test for the graph of a relation, really, to determine whether the relation represents a function. And we're interested in domain range. We're interested in where the function is positive and when the function is negative. We are also interested in the xy intercepts of the graph if they exist. So let's begin with this example that I have on there. In this example, we're given the graph of a function, right? And we have a number of questions we want to answer. First of all, we want to find the value of the function at 0 and negative 6. So let's do it this way. What if I say part A, we're going to do f at 0. Now, f at 0, that means when the function has a value of 0, right? So f at 0 means when x is 0. Well, when x is 0, the value of the function is on the y-axis. That would be 3. Okay. All of the information, we're going to get them directly from the graph. Oh, first, the vertical line test. I didn't mention that. This graph represents a function, the graph of a function, because the vertical line test says if you draw a vertical line anywhere on the graph, it should cross the graph at one and only one point. So this is clearly a function. There's a relationship. The graph represents a functional relationship. One that would not, for example, would be like this. Let's say I have a sideways parabola. In this case, the vertical line test tells us that this graph does not represent a function. And the reason is simple. When we talk about functions in the beginning, previous section, we mentioned the first components of the ordered pair must be different. So just going to throw in some numbers here. Suppose this point has coordinates 3, 3. This point has coordinates 3, 6. First number x, second number y. Now look at the first numbers. See, they are the same. So any vertical line that's drawn, if it crosses 2 or more points, that would imply the points are collinear. And for the vertical lines, that means they have the same first x components. And that is why the vertical line test works. Okay, so this is definitely a function. The graph is that of a function. And of course, we're told given the graph of the function. But if we're not told that, we can always determine that ourselves. Now, let's continue on. F at negative 6. So you go to x negative 6. That would be right here. And there you go. The function value is negative 3. So f at negative 6 is negative 3. In part B, find f at 6. Well, f at 6, this time you go to a positive 6 and you kind of reach below until it touches the function, and judging from this one, because I would say right here, negative 1, let's agree on negative 1 being the value of the function. Okay, now f at 11, the value of the function at 11 when x is 11. So when x is 11, again, you go up until you touch the function, the value is 1. So f at 11 is 1. Remember, the y values are what the outputs are here. Okay, now what else? Let's continue on to part C. In part C, if f at is f at 3 positive or negative? Well, f at 3, somewhere in here above the x-axis, the y's are positive. So f would be positive in this case. In part D, is f at -4 positive or negative? Well, at -4, now you have to go to -4 and do the same thing until you reach the function. The function is below the x-axis, so y would be negative, therefore f is negative. Okay. In part E, for what values of x is f of x 0? Remember, f of x means y. Y is 0. There's a 0 here, there's a 0 here, and there's a 0 here. These happen at -3, at 6, and at 10. So the answer to part E, for what values from left to right? X equals -3, and then we have 6 and 10 for those values of x. In part F, for what values of x is f of x positive? Now this time y is positive. So if I draw a line here, and you're looking at positive values of y here, and you look at the positive value of y right there. Correct? So for what values of x? Well, to capture this part, looks like in part F, for x between -3 and 5, correct? The function is above the x-axis, and between 10 and 11, and x between 10 and 11, the function is positive. Okay. Now, you could include equalities in these. It really is the choice of the author, and some authors include it, others do not include it. But we're going to exclude them because, strictly speaking, greater than 0, right, means do not include 0. So it has to be great. In this case, you don't include the equality. So let's not include the equality, because if it's equal to, it will be exactly equal to 0. Let's do part G. What is the domain of the function? Domain means all possible x values. Well, x starts from -6, ends at 11, right? Starting and ending. So domain is going to be bracket -6, comma 11, close bracket. In brackets means it includes it. And because we actually have a solid dot here, means the point is included. Sometimes they use open circle, means you exclude it. In that case, I would use a parenthesis. So there you have part G. That's the domain of the function. In part H, what is the range of the function? For range, you look at the y values. So notice the function has values along the y-axis anywhere. It looks like I'm bounded between -3 and 4, right? This is -3 and this is 4 on the y-axis. And we're going to go with that. So the answer to this is going to be from -3 to 4. And we always, in interval notation, we go from low to high. There's part H. In part I, what are the x-intercepts? X-intercepts are places where the graph crosses the x-axis. So it looks like we got 3 of them. The x-intercepts are at -3, 0. The other one is at 6, 0, and the last one is at 10, 0. Notice all those have y that is 0. So for x-intercept, y will be 0. Let's do part J. What is the y-intercept? Now the y-intercept, the place the graph crosses the y-axis. And these are 0, 3. Now, just the point here, these are coordinates of a point in parts I and J, x, y. Whereas here, these are intervals. In part G, those are intervals. It's confusing because, for example, if, let's say part F, I can write x between 10 and 11 like this. Here I mean it as an interval, the parentheses. We're talking about intervals, whereas here we're talking about points on the Cartesian coordinate system. So it could get a little confusing here. Hopefully you can sort this out. All right, we did part J. Let's do part K. In part K, how often does the line y equal a half intersects the graph? Now y equal a half. This is going to be a horizontal line drawn at 1/2. Right? So it's going to be here somewhere. Draw a horizontal line at 1/2. How often? Once, twice, 3 times. So it's going to cross the graph 3 times. True? How often does a line x equal 5 intersects the graph? Okay, x equals 5 would be a line at 5. Remember, x equal the constant is a vertical line at constant. Once. So the answer to part L is going to be once. One time, or just once. Let's do M. In part M, for what values of x does f of x equal 3? F of x means y. So for what x is y is 3. So you go to y 3 here and y 3 here. Those are the 2 places. Twice. It says for what values of x. So the values are 0 and 4. At both of those, y would be 3. And finally, in part N, for what values of x does f of x equals -2? Remember, f of x is y. So y equal -2. For what values of x? Well, a couple of values. -5 and 8. And 8. For those 2 values, they have exact same y values. And there you go. The kind of things we're interested in this section. Now, for these next 2 graphs, we're actually going to do the following. We want to find the domain and range. Okay, so here's an example. Let's do domain and range. The domain of this function, all possible x values. Notice it can go there forever, right, indefinitely, so your x's keep going on the left side. So my domain is going to be from -infinity up to 0, including 0. In interval notation, you always go from low to high. Okay, whether it's bracket, parentheses, whatever, doesn't matter. Always go from low to high. So -infinity is the lowest, lower than 0 anyway. So you go from -infinity to 0. What about the range? The range is the y values, right? Same thing. This thing goes gradually to infinity on the y-axis, -infinity on the y-axis as well. So the range is from -infinity to infinity. Although slow and gradual, but eventually it will get there. Okay, so we got the domain and range. Now, what about the intercepts? Let's look at the x-intercept and the y-intercept. The x-intercept is 0, 0. Anytime x-intercept is x is 0, y is also 0. So in this case, they're both the same. There's only one place the graph crosses the x-axis. It's exactly the same place it crosses the y-axis. Now, usually also with functions, the graph of functions, we're interested in symmetry. So let's see what kind of symmetry there is. In this case, look at the upper branch is the mirror image of the lower branch and vice versa. So this would be example of symmetry with respect to the x-axis. Okay. If you want, for example, symmetry with respect to the y-axis, there you go. This would be an example of symmetry with respect to the y-axis. So if you fold one branch of this parabola around or about the y-axis, the two branches overlay one on top of the other. So this would be with respect to the y-axis. And the other kind of symmetry that we often look for is symmetry with respect to the origin, which is a single point. So for instance, let's say I have this nice looking curve, then I have the same nice looking curve this way. And the way I have it is intended so that, for example, a point here that is xy is also going to be negative x, negative y on the other part of the graph of that function. Okay, that would be symmetry with respect to the origin. Okay, a single point. This point, for instance, symmetric to that with respect to the origin. All right, so for the one we just looked at, there's only one symmetry with respect to the x-axis. Now let's look at this last example here. And this is supposed to be negative pi, by the way, because it's to the left of 0. For this one, let's do the same things. What are the domain and range? Well, the domain, possible x's, it goes from negative pi to pi. Negative pi to pi. And I'm sure some of you recognize this as the graph of, like, it would be sine or cosine. This is actually the graph of sine because it's at 0, 0. Cosine starts at 0, 1 like that. Right? We'll get to those later in about 3 weeks. Okay, and there you have it. Domain from negative pi to pi. Now, what about the range of this? The range is possible y values. This thing is range bound between negative 1 and 1, right? There is no value higher than 1. There is no value on the graph lower than negative 1. So the range is going to be from negative 1 to 1. And always remember, for domain and range, we write them from low to high, okay, in the interval notation. What about the intercepts? Let's go x-intercept. Let's do y-intercept. Well, the x-intercept, y-intercept happen to be, again, one of them is the same. X-intercept is at 0, 0. The other x-intercept is at negative pi 0, and the other one at pi. Any points where the graph crosses the x-axis is called the x-intercept. The y-intercept, if you have a function, by the way, there's no way you can have more than one y-intercept. It will not be a function. So usually there's only one point, 0, 0. And again, with function, it has to be a single point. The question is how high or low it is, above or below the x-axis. In this case, it's exactly the y-intercept is exactly on the x-axis. Okay, got the domain, range, x, y intercepts. Let's do our symmetries. This thing, is it symmetric with respect to the x-axis? Well, if it's symmetric with respect to the x-axis, then that means, like the one above it we just did, that means this portion has to have a reflection here. And that defies the definition of a function. So functions will never be symmetric with respect to the x-axis, because if they are, you can look at this one. If they are, they fail the vertical line test, right? So functions are never symmetric with respect to the x-axis. But they could be symmetric with respect to the y-axis. Not saying this one is. If this one was symmetric with respect to the y-axis, then this part would probably have to look like that, right? Also, to be symmetric. Or the upper arch should look like this, also on the other side. That would be symmetric with respect to the y-axis. So no symmetry with respect to the x-axis, not with respect to the y-axis. what about with respect to the origin? The origin being this one. Now, look at this one. Let's say a point here. This point has coordinates pi over 2 and 1. And this point, which is like a mirror image with respect to the origin. This one is going to have negative pi over 2 for the x and negative 1 for the y. You see that? That's exactly what I have here. If a point xy is there, so is negative x, negative y. For example, the mirror image of this point with respect to the origin is going to be here. Thus, this thing is symmetric with respect to the origin. So we're going to say symmetric WRTO with respect to the origin. And the origin, of course, is 0, 0. Again, in this course, if there's symmetry with respect to a point for us, it's going to be the origin. Okay. And that's pretty much all I wanted to talk about in this section. So we are done with section 2.2, graphs of functions. We will look at graphing techniques or graphing functions in a greater detail later on. So this is just to kind of give you some ideas about the graphs of functions. And with that, we will conclude this lecture. Thank you for watching.